My name is Emil Eifrem from Neotechnology. So, NoSQL. First off, the name. Everyone hates the name, right? People think that it means never SQL or not SQL or no to SQL, but nothing could actually be further from the truth. NoSQL is actually not only SQL, as in the observation that the backends of the future will consist of not only SQL databases, but also key value stores and graph databases and document databases. NoSQL is one of the really hyped words right now, and as such, a bunch of projects want to attach themselves to the name. So there seems to be, a new NoSQL project every week these days. But if you squint a little bit, you can see that there's 4 emerging NoSQL categories. The first one is the key value stores. And the key value stores, they're all inspired or based on a research paper published by Amazon called Dynamo. And Amazon basically said a couple of years ago that, hey guys, we pushed our system to levels of scalability that few others have been able to do. We're one of the top tier web properties in the world. And we did this not by using only an SQL database, but we also had to build our own database. And that database we called Dynamo, and here's how it works. And then they spelled out basically a global distributed hash table, which is now called the key value store. And the data model of a key value store is that of a hash table. If you're a Java guy, java.util.map is a reasonable abstraction. If you're a Python guy, it's a dict. Basically an associative array. You have keys, and those keys map to a value. That value may be sort of a compound content, but really from the point of view of the key value store, it's opaque. Example implementations here are React, Project Voldemort out of LinkedIn, and then Tokyo Cabinet and Tokyo Tyrant. So that's the first category. The second category is the column family or big table clones. And these are all based on Google's big table paper. And they basically did the same thing as Amazon. They said that, oh yeah, and by the way, we've also managed to push our systems to reasonable scale. And actually, we also did this by not just using a SQL database, but also alternative implementations. In fact, we had to build our own, and we called it Bigtable. And the data model of Bigtable is creatively that of a big table. So it's a large tabular abstraction, but the unique thing about Bigtable is that every individual row can have its own schema, at least in theory. So you can have one row which has 5 or 6 columns, and then the next row might have 2 or 3 columns. So that's a really powerful way of capturing so-called semi-structured information, which has a few mandatory attributes but many optional attributes. Example implementations here are HBase from the Apache Hadoop project, Hypertable, which is a C++ implementation. Other than that, it's equivalent to HBase. And Cassandra. And Cassandra is probably the most popular column family or big table clone out there today. So that's category number 2. And then the third category is document databases. And these, the first document database that got really popular a few years ago was CouchDB. And CouchDB is inspired actually by Lotus Notes, which, while it may not be the most amazing email client out there, actually has a pretty interesting backend. And that backend uses a collection of key value pairs as the main abstraction. And those collections are called documents. And they're typically expressed as JSON. At least that's the language of choice for CouchDB. That they took and sort of ported or took the mentality and the thinking and the philosophy from the Lotus Notes backend into the web era and added a RESTful API, added JSON, and added JavaScript views. The most popular document database today is called Mongodb. Many of you have probably heard of it. And it's basically the equivalent of CouchDB, but it's written in C++, and it has client-side drivers and a bunch of other things that make it more convenient for many people to use. So that's the third category. And then the fourth category, and obviously my corner of the NoSQL world, is graph databases. And sort of tongue-in-cheek, it's inspired by Euler, the 17th century mathematician that invented graph theory. So it's been around for a while. And the data model here is actually very equivalent to the document database, where the document database had JSON documents, so the documents were key value pairs. Those are called nodes in the graph database model. So the nodes can contain key value pairs, but then on top of that, you have typed relationships. So you can say that this node here is related to this one node through the type knows. So they know one another, or owns. This node owns this other node, or is contained in, or whatnot. You can also, and this is really powerful, and we'll obviously talk more about this later, you can also attach key value pairs to the relationships as well. Examples here: Allegro Graph, Sonus, and then obviously my favorite, which is Neo4j. So NoSQL is all about scalability. Everyone knows this. But what is less, I think, understood, or at least less appreciated today, is the fact that there are two axes to scalability. One is scaling to size. And that means, how does your system cope with more and more information that is uniform, that looks sort of similar to the other information stored in the system. The other one is scaling to complexity. How does your system deal with more and more messy data? And messiness can be semi-structured data, so few mandatory but many optional attributes, fits really poorly into a table. Or it can be very connected data, so lots and lots of connection arbitrarily and ad hoc in the data structure. And if we look at these four categories, we see that the key value stores are all the way to the left on complexity, so really, really weak on complexity, but awesome at scaling to size. This is because the key value store has a very simple, some people even call it a simplistic data model. It can contain only key and value pairs, and that's it, which makes it really, really simple to get it to scale across many, many machines, but makes it really difficult to handle data that is not just key and value oriented. Then maybe the column family guys are slightly better at handling complexity because they can handle the semi-structured information that we talked about before. If you recall, every row in the column family or big table can, in theory at least, have its own individual schema. And then we have document databases, which are even better at handling complexity, and all the way to the right are graph databases, which are awesome at handling complexity of data and really modeling the real world in a very intuitive way, but are the most challenging to get to scale to size. And as many of you may know, the enemy of scaling to size is coupling in data. If data is very connected, it's very difficult to get it to partition across many machines and get it to scale horizontally. And since graph databases are awesome at handling this sort of connected data structures, it becomes more difficult to get it to scale across many, many machines. However, the interesting point here that is, why we like to talk about graph databases, because if we could very simply be a document database, it's very easy to transform a graph database to a document database, is that 90% of the use cases or more subjectively out there is substantially below the scalability capabilities of graph databases and document databases. The interesting aspect about that is that if you're at a point where your system can't can't cope with the scalability requirements of your application, if your database system can't do that, then that is a really challenging situation to be in, obviously, because you have runtime performance problems. Having said that, if you have a system that can handle your scale in terms of size, the only thing you care about as a developer is scaling to complexity, because that means that you're going to have to do much less work up in your application layer in modeling your domain, because you have such an expressive and rich data model back